The X-15 Flight Research Program, a joint venture of the National Aeronautics and Space Administration, the United States Air Force, and the United States Navy, is conducted by the NASA Flight Research Center located at Edwards Air Force Base in California. The three X-15 research vehicles were designed and built by North American Aviation. The liquid rocket engine, designated YLR-99, is a product of Reaction Motors Division of the Thiokol Chemical Corporation. Designed to reach an altitude of 50 miles and a speed of 4,000 miles per hour, the X-15 has already exceeded both these limits. The X-15 research vehicle explores the flight regimes where fundamental data applicable to the problems of manned hypersonic and space vehicles can be obtained in full-scale flight. The research program conducts studies in the area of vehicle performance, aerodynamic heating, flight control and control systems, physiological phenomena, and vehicle systems, providing basic information in advance of design needs for future space missions. A typical X-15 flight begins at the hangar, where early on the day prior to flight, an intensive checkout of the X-15 internal systems is performed. Some of these are the propellant system, the auxiliary power unit which supplies hydraulic pressure and electrical power, the navigational and data systems. The check successfully completed, the aircraft is towed to the engine run-up stand for engine check. On the stand, the pilot's schedule for the flight operates the engine for a test run of approximately 30 seconds. Advancing the throttle to maximum power as indicated by the expanded shock diamonds and the flame pattern. And reduces power to minimum throttle, indicated by the diminished size of the shock diamonds. A successful conclusion of the test stand run proves the aircraft is ready for the designated flight. Water on the pavement is necessary for cooling and to minimize contamination. The mating of the X-15 to the B-52 begins as the aircraft is rolled into position under the wing. Aligned on the jacks, and the nose gear is positioned on the hydraulic lift. Raised by hydraulic equipment, the X-15 is tucked up in the pylon and the locking hooks are engaged. The hooks are mechanically interconnected to assure that all will release simultaneously. Final adjustments are now made prior to the engagement of the lock. The X-15 positioned on the pylon and the final checks completed. Early on the morning of the day selected for the flight, the servicing crew takes over. At this stage, liquid oxygen servicing is completed, as indicated by the overboard spillage of the vents, appearing like ground fog. The liquid oxygen oxidizer, gas services for the propulsion system, breathing oxygen, ventilation and pressurizing nitrogen, all have been serviced before the arrival of the truck containing anhydrous ammonia, the fuel used in the X-15 in combination with the liquid oxygen. Safety precautions require the servicing crew to wear protective equipment when transferring anhydrous ammonia because it's extremely toxic when in concentration. Now, some people get nervous when they're on camera. Missed on the first try, so let's try it again. That's better. The safety equipment consists of protective coveralls, gloves, protective mask, and auxiliary breathing supply. An interesting feature of the ammonia servicing process is that the filler is at the rear end of the tank. The ground attitude of the B-52 causes the X-15 to hang tail low. So the rear end of the B-52 must be jacked up to level the X-15 and assure a full load of fuel. Attachment of the fuel service hose and ground connection is now being completed. As the fueling proceeds, the pilot is in the van nearby, having his physiological leads attached and checked, and his pressure suit put on and checked. This procedure takes 40 minutes before the pilot is ready to enter the X-15. The checks continue as his electrocardiogram, breathing rate, suit pressure, and helmet pressure measurements are taken and recorded. The restraint harness is integral to the coverall flight suit worn over the pressure suit. Attachments at each shoulder and each hip fasten him snugly into the seat. Like a bronc buster settling in the saddle, the pilot joggles back and forth in much the same manner, as the straps are adjusted to assure proper restraint and still allow sufficient freedom of movement to reach everything necessary in the cockpit. It's obvious that the pilot cannot fasten himself into the seat without assistance. Now securely fastened, the suit is again checked on the X-15 systems, and a series of checklist items are completed. The canopy is closed and the pilot gets the hand signal, everything okay. The pilot, now breathing 100% oxygen, and the launch panel operator and the B-52 jointly get the inertial platform navigation system and the attitude presentation operating. All pre-flight checks completed, the B-52 pilot taxis to the takeoff runway. The upper fin of the X-15 extends through a notch in the trailing edge of the B-52 wing, so the flaps of the B-52 cannot be used for takeoff or landing. The ground support vehicles are soon left behind as the B-52's speed rapidly increases. On a hot day, more than 12,000 feet of runway is required to achieve liftoff at 170 to 180 knots. Snugly tucked in the X-15 cockpit, the pilot is no doubt recalling the good old days before wing mounting, when he had to squeeze into the cockpit down through the bomb bay. This maneuver was accompanied by considerable huffing and puffing, and a big sigh of relief when he was finally strapped in the seat. Nothing to do now but sit back, relax, and mentally help the B-52 pilot with his flying. Wing mounting of the X-15 permits the ejection seat to be utilized in an emergency, while the aircraft is still attached to the B-52 shackles. All flights are monitored by a central control room, where a group of engineers, each associated with a specific aircraft system, monitor telemeter data. The X-15 pilots, when they're not flying, serve as ground communicators in the central control room. Shown here is X-15 pilot Major White and the assistant flight controller, in communication with the flight pilot, Joe Walker. On each flight, chase planes accompany the B-52 X-15 combination from takeoff to launch. The chase pilots monitor the external appearance of the X-15 and by radio assist the pilot in the conduct of portions of his pre-launch checklist. A prime operation is now taking place as the pilot chills down the oxygen system of the engine. Later on in the flight, other chase planes spaced along the flight path at intermediate and destination dry lakes will join the X-15. Launch checks continue as the pilot tests the attitude control rocket, the high-altitude control system used when the X-15 is on an altitude flight profile above the usable atmosphere. At extremely high altitudes, the conventional aerodynamic control surfaces are not sufficiently responsive for complete flight control. So attitude control rockets are necessary. Pitch and yaw rockets are located in the nose. The roll rockets are located on each wingtip. The underside of the X-15 is now building up a coating of frost on the outside of the liquid oxygen tank due to the intense cold of the liquid oxygen at a temperature of minus 300 degrees Fahrenheit. The auxiliary power units are now started. Note the exhaust trail going over the horizontal stabilizer. The pre-launch test of the control system, the electrical system, and the hydraulic system is completed. The engine pump is started, and the rocket engine igniter is started. The X-15 is now in ready launch condition. The physiological monitoring officer, the stability control monitoring engineer, and other ground control personnel record continuous telemeter data, radar tracking, and voice transmissions throughout the flight. Radar records on the ground track map the progress of the X-15 relative to the flight plan, enabling course corrections to be relayed to the pilot. Synchronized stopwatches in the X-15, B-52 chase planes and ground control stations start clicking at the moment of launch. Flight roll-off occurs as the shackles release. The X-15 engine is started, and the aircraft accelerates rapidly, quickly leaving the B-52 far behind. On this flight, the plan called for a buildup of 1,500 pounds per square foot of dynamic pressure before pull-up. 6 motion picture cameras are carried aboard the X-15. 4 are mounted on the fuselage facing to the rear. 2 are mounted in the cockpit. They are located at camera number 1 upper right, number 2 upper left, number 3 lower right, number 4 lower left, number 5 behind the instrument panel facing pilot, number 6 behind pilot facing instrument panel. Again the launch, photographed by X-15 camera number 1. Note the rapid acceleration as the aircraft drops away from B-52, and the steep climb-out angle. The speed brakes are extended to permit longer burning time of the engine propellants and provide added aircraft stability during re-entry. Peak altitude of 317,000 feet planned for this flight is now achieved. X-15 camera number 5 shows the pilot's reaction to zero-G state. Camera number 6 shows the control panel and the weightless condition. Note the pages on the pilot's flight checklist. The planned peak altitude accomplished, the aircraft starts on the downhill side of the parabola. As the descent angle increases, the horizon gradually disappears out of the picture. Now the pull-out to level flight, and the horizon once again is seen behind the tail of the aircraft. The pilot banks the X-15 to visually judge for himself the landing site relative to his position. The speed brakes close and the pilot guides the aircraft into an approach pattern for a landing on Rogers Dry Lake. Residual propellants are jettisoned prior to landing to relieve the aircraft of all excess weight. The lower portion of the vertical fin, which extends below the landing gear and would consequently dig in on touchdown, is jettisoned with a recovery parachute attached. At a pattern speed of 300 knots, the pilot reserves the extension of the landing gear and flaps to avoid drag increase until the landing is reasonably well assured. Because the main landing skids are located far back in the fuselage, the pilot cannot hold the nose up on touchdown, resulting in a rather jarring contact of the nose gear to the ground. Touchdown is made at a sinking speed of approximately 2 feet per second and a forward velocity of 200 miles per hour. The average slide-out distance is 5,000 to 6,000 feet. Brakes are not necessary with this landing gear configuration, as the skid ground contact serves to slow down the aircraft. Landing successfully completed, the ground support equipment and personnel necessary to deactivate the systems approach the X-15. Assist the pilot in getting out of the cockpit and prepare the aircraft for transport back to the hangar. An aerial view from a helicopter shows the support equipment at destination required to conduct an X-15 flight operation. The ground crew has finished the initial details of aircraft recovery, and the post-landing checklist is almost complete. Relieved of his helmet, pilot Joe Walker is happy to hear that welcome greeting. "That was a good one, Joe." And he obviously agrees. Willing hands disconnect his leads and assist the pilot from the cockpit. The flight tension's over. The relaxed pilot enters the van to have his flight suit removed and post-flight physiological checks completed. Successful missions of the X-15 are indicated by the symbols painted on the van. The B-52, affectionately known as the High and the Mighty One, roars over at a low altitude and executes a Chandelle maneuver to announce mission accomplished. And so ends another X-15 flight mission, adding more basic information and scientific knowledge to our space effort and increasing man's capability to reach his ultimate goal, the conquest of space. Throughout the ages, men of courage have dared to explore the unknown. History records the voyages of Magellan, Balboa, Cabrillo, Columbus, and other navigation pioneers who faced and conquered the unknown dangers of the ocean's horizon. Today, in this age of scientific and technological development, man is again accepting a challenge to explore the last frontier, space. The penetration of the universe is being accomplished by men of greater courage and vision than the explorers of history. Our successes in near space have been accomplished by men who are not accompanied and encouraged by an entire ship's company, but instead faced and conquered this alien environment alone. Basic research furnishing a constant flow of new knowledge and scientific data is the keystone of the success of the NASA space program. The successes already achieved in space, the further successes in more complex and spectacular space missions which man is destined to accomplish, will depend in large measure on the continuing flow of new scientific data, contributed by such research programs as the X-15. For its many valuable contributions to our space effort, much credit is due to the personnel of the X-15 research program, to the scientists, the engineers, and technicians, who each in his own way has subscribed to its success, to the pilots of NASA and the United States Navy, the United States Air Force and North American Aviation, whose skill and resourcefulness has also contributed to that success. They are the architects whose pioneering has helped to build the first steps on man's pathway to the stars.